Welcome to Lecture 19, Polynomial Approximations. Let's start with some motivation. So recall, probably from your first semester calculus class, that you can always approximate a function, it should be a continuous function, near a point x equals a using the tangent line. So to see how this works, let me just sketch a function. Let's just do something like this, and let's say this is the point a. So this point up here, this value is going to be f of a. So the tangent line is going to look like something like that. And the idea is if you zoom in close to here, so if you zoom in really close here, locally, that function is going to look flat. So analytically, we say that so the derivative f prime of a is approximately equal to f of x minus f of a over x minus a. So what I mean by this is let's take an x that's here that's really close to a, and then so this value is right there. That is exactly f of x, but using the tangent line approximation, so at this point x, this red dot is the value on the line. So this value here is going to be approximately equal to f of x. And again, this only works for x close to a. Once we get far out, once we're out in this range or way down here, then these two lines are going to diverge enough that this is not a good approximation. So again, only close to. Let me zoom in here. Let's suppose I were to zoom in here close. What you would see is you would see that our function looks almost flat, and our tangent line is going to be, again, it's going to be really close to it. So what we're doing is that's going to be, so maybe this is a down here. This might be x. And this point is really close to, so this is exactly f of x. And this point here is really close to it. So this error right here is very small. Okay, so we conclude from this equation. So what we can do is we can solve for f of x, and we can say that f of x is approximately equal to f of a, I'm going to run out of room here, plus, let me make it smaller, plus f prime of a times x minus a. Okay, so now where does this come from? And let me give this a name. Let me call this t1 of x. Okay, so where does this come from? So what I've done is I've taken this equation, and I'm pretending for a moment this is an equal sign, and I'm just going to solve for f of x. So I multiply this over to that side, then I add this over here, and I get f of x is approximately equal to this thing here. So what this should remind you of, look at this. This thing should be like your y equals mx plus b. So let me draw that up here. So think of this as f of x being approximately mx plus b. So notice that this is your m. So m times x, and then your b, well, here's your b, and I guess you also have this number times that number. So if you were to collect terms, you could say this is equal to, I'm sort of improving here, f prime of a times x, and then this is your m times x, and then what's left over? So we have f of a plus, not plus, that should be minus. Let me erase that. So that should be minus a times f prime of a. So notice this is my mx and this is my b. So a little bit of a review. You've seen this before, and I'm just introducing you to what we're going to do in this section, which is we're going to take this a step further. So takeaway point from this slide is, given any continuous function, if you pick a point A, say, you can zoom in close enough, and that function looks like a degree 1 polynomial, which is a straight line. So you can always approximate a continuous function with I should say differentiable, but that's not important right now. But you can always approximate f of x if you zoom in close enough with a degree 1 polynomial. Now what we're going to do is we're going to extend this. We're going to approximate functions with degree 2 polynomials and degree 3 polynomials and degree 4 polynomials. And the higher and higher the degree gets, the better our approximation is going to be. And where we're going with this is eventually we're going to approximate a function, or sometimes not even approximate, but we're going to exactly write a function as an infinite series, so as an infinite sum. Think of it as as infinite degree polynomial. You can casually think of it like this. Okay, so let's actually do an example like this. Okay, so let's do a real example now. Let's approximate the function cosine of x near x equals 0 using a linear approximation. Okay, so we know what cosine looks like. It looks something like this. And the tangent line is going to look something like this. And so this blue line is the linear approximation. It's if you zoom in at 0, so if you zoom in right here, locally this graph looks flat. And so the next part is we want to estimate. So that's the first part. We approximated this using the line. I mean, I guess I could say that this is the line y equals 1. And then we want to use this to estimate the values of cosine of x for three different values. One of them is going to be really close to 0. The other one, 0.4, is going to be out a little bit more. And then pi, that's a terrible approximation. That's going to be out here. And as you can see, tangent line doesn't come close to cosine of pi. Cosine of pi is -1. Cosine of, and this line evaluated at pi is equal to 1. Okay, so recall from the last slide, we said that the tangent line approximation, we get out a formula from it. F of x is approximately f of a plus f prime of a. I should be putting zeros here instead of a, but well, that's okay. Okay, so here a equals 0, f of 0, cosine of 0 equals 1. What's the derivative? So we need the derivative. F prime of x equals negative sine of x. And so that means that f prime of 0 equals, be careful, 0. Basic trick. Okay, so our straight line, let's use this formula. I mean, again, we know what we should get. We should be getting y equals 1, so let's check. I use blue again. So f of x is approximately equal to f of a, which is 1 plus 0 times x minus 0. And so that, of course, just goes away. So yeah, f of x is approximately equal to 1, and this only works close to 0. So using this approximation, I can say that f of 0.5 is well, let me erase that. Let me just say one more thing. That is equal to cosine of, oh, I'm sorry, I said 0.05. The problem actually says the problem says 0.05. So cosine of 0.05, and this is the actual value of this, if you were to get out your calculator, is 0.99875, and that's really darn close to 1, which is what our approximation says. So again, it's hard to actually draw this to scale, but if I were to take this and I were to blow it up, what you would see is, you would see something like, you would see the tangent line approximation being like that, and you would see that the function is like this. And so what we're doing is we're saying so this is at 0, and this might be at 0.05, and our actual value is 0.99875, and our approximated value is 1. So this error is really small, because we're close to our point A equals 0. Okay, so next, f of 0.4. This is equal to, again, exactly equal to cosine 0.4. Again, now we're getting further away from, so this is 0.4. The other one was really close to 0. So we can see that our approximation is going to be a little bit worse. We're going to have bigger error. So cosine of 0.4. It's not going to be that bad. It's if you do the math, I did this ahead of time, it's 0.921. So 0.4 is close to 0. It's not as close as 0.05. I guess I've exaggerated a little bit on this scale. 0.4 should be closer, but I can't draw it with any more precision. So again, this is a pretty good approximation because 0.4 is close to 0. Lastly, let's do f of pi. This is the last part. This is cosine of pi, which is -1, and this is not close to 1. So this is not anywhere close to 1, and that's not a surprise, because maybe we could have gotten lucky, but we should not expect that our linear approximation is going to work. Here's pi out here. We shouldn't expect that our linear approximation is going to work outside of a small neighborhood of 0. It might, we might get lucky, but we can't expect that. Okay. So what's better than a linear approximation? Well, linear is just a degree 1 polynomial. How about a quadratic approximation? So now we're going to generalize what we did before with not just a tangent line, but a tangent parabola. So approximate cosine near the origin using, so now we have more freedom. Instead of just mx plus b, we have, we're going to have 3 constants. So let's write this down. So a quadratic polynomial is going to be of the form, let's call it t2 of x, for degree 2. So now there's going to be a constant. This is the y-intercept. There's going to be a c1x, and there's going to be a c2 x squared. So this is an arbitrary degree 2 polynomial. And now recall that our arbitrary degree 1 polynomial is, well, I'm going to write it as mx plus b. How about b plus mx? We're so used to using these m's and b's, these constants, but I'm going to step back and use c0, c1, and c2. Okay, so how do we do this? Well, let me sketch this. See if I can do it for. Okay, so first of all, what is a quadratic approximation going to look like? So here's what our function looks like. This is cosine of x. Now a parabola, we know cosine of x is going to go up and down and up and down. And a quadratic function or a parabola can't do that. The best we could hope for is that our function exactly equals cosine at this point, and it's a parabola, so it's going to look something like that. And again, that's really the best we can hope for. So it's got to have the same y-intercept, and what that means is that t2 of 0, the y-intercept, has to be c0. Again, these things have to have the same y-intercept. And again, well, what is c0? c0 is 1. So the y-intercept of this function, just like the y-intercept of cosine of x, so this is f of 0, cosine is f of x. So these things have to have the same y-intercept, which is, so f of 0 has to equal t2 of 0. But we need more too. We want the slope of the tangent line of cosine to equal the slope of the tangent line at this polynomial. So what does that mean? That means that t2 prime of 0, the slope of the tangent line of our polynomial approximation, that has to be the same thing as p prime of 0. And that, just by looking at the picture, that has to be 0, because we know that cosine, the derivative of 0 is going to be 0, the derivative at 0 is going to be 0, so that means that has to be equal to 0. And by the way, what is this? T prime of 0. Let's do this in our head. This is t2 of x. Let's take a derivative. That goes away. This 2 comes down, and the constant term is c1. When we plug in 0, the constant term is the only thing that remains. So this has to be c1. And finally, we also want the second derivative of both of these functions to be the same. This is going to be a recurring theme. When we want to approximate a function using a polynomial, or using some other function, which I guess it's always going to be a polynomial, we want them to agree on every single derivative. So we want the 0th derivative just means the y-intercept is the same. The first derivative just means that their tangent lines are the same. The slopes are the same. The second derivative means a little bit more, that the, I guess, acceleration, if you want to call it that, are the same. So let's carry this one further. So they have to agree on every single derivative. And we can do that because every time we take derivatives, we're going to get a constant, and we're going to get one of these little guys popping out. And we don't know what these are, so we can set these to be anything we want at will. So t double prime, or t2 double prime, the second derivative better be the same as the second derivative of cosine. And now the second derivative of cosine is negative cosine. Plug in 0, you get negative 1, so that's going to be negative 1. And now, let's pause a moment. What is the second derivative of t2? If you take two derivatives of t2, that goes away, that goes away, and the only thing left is this term, but this x squared turns into a 2. So in other words, this is going to be 2c2. Let me just pause to say that this is equal to the t prime. This is just t double prime, or t2 double prime of x, and also t2 double prime of 0. So we got to solve for this. So solve for this equation. That's easy. We get that c2 equals negative 1/2. Yeah, just negative 1/2. So putting this together, now this is going to be, and we're trying to figure out what function is this blue curve. That's a polynomial. We know it has y-intercept equal to 1. We know that the slope of the tangent line at 0 is 0, and now that's just c1, and now we know what c2 is. So we actually know this function. We can say that, we write it like this, t2 of x equals 1 plus 0x minus 1/2 x squared. All I'm doing is I'm just filling in our known values of c0, c1, and c2. So let me just simplify that as 1 minus 1/2 x squared. So in other words, the best fit line, not line, the best fit parabola, or the best quadratic approximation to cosine of x is going to be precise is this blue polynomial, which is this thing right here. Now notice if I had picked a different point instead of x equals 0, if I had wanted to do this at, oh, I don't know, let's say x equals, suppose I wanted to do this at pi, then we're going to have a different polynomial. I don't know what it would be, but it would probably look something. It would probably look something like that if we wanted to approximate at that point. Okay. So you can probably see where we're going here. Increasing the degree of the polynomial approximation improves the approximation. So we can ask the same thing about a degree 3 polynomial or a degree 4 polynomial. So let's think here. A degree 3 polynomial, are we going to get anything better? I mean, if we have a degree 3 polynomial, that's going to be asymmetric, right? It's going to look something like that. And I claim that even if you allow yourself to have a degree 3 polynomial, you're not going to get any better than this. In other words, the best degree 3 polynomial is still the best degree 2 polynomial. It's this parabola right here. Allowing yourself to have an x cubed doesn't actually help your approximation. Maybe it's not obvious, and I'm not claiming it should be, but think about that. Keep that question in the back of your head when we do Taylor series, and you'll see some more connections. But let me say one more thing here. See if I have a different color to go off of. Yeah, I think I do. I haven't used this color before, but let me try green. So what if I say find the best degree 4 approximation to cosine of x, centered at 0? What's that going to look like? So now degree 4 polynomials, they're allowed. Some of them look like parabolas, but they're also allowed to have humps like this. So I'm not sure exactly, but I would bet that with the degree 4 polynomial, we could probably do a lot better. We can probably do something like this, and we can approximate this first hump pretty good. Not perfect, but pretty good. And again, if you were to allow a degree 6 or degree 8 polynomial, you can probably approximate the first few humps pretty good. And then as you allow yourself to have higher and higher degrees of approximations, in the limit, you can approximate this function exactly. So that's sort of a preview as to what's coming next. So the key idea here is that increasing the degree of the approximating polynomial improves the approximation. Okay, so these approximating polynomials, they have a name. They're called Taylor polynomials. Formally, the Taylor polynomial of order n approximating f of x near some point a, so sometimes we'll say centered at a, is this creature here. And so, again, a picture of this. So before we've been doing this at 0, but you can really do this at any point. Let's say that this is a, and we want a nth order polynomial that approximates this function at a point. So I'm not going to formally prove this, but I'll go over why this is true. So this polynomial, Tn of x, this is going to be, it's a polynomial of degree n. So it's going to be c0 plus c1 x minus a. If you don't like the a, just pretend a is 0. That's what we did in the examples before. So plus c2 x minus a squared plus c3 x minus a. Ooh, there's a typo up here. That should be a 3, not a 2. X minus a cubed plus dot 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 plus cn x minus a to the n. So the idea, where this definition is coming from, is the fact that these things are equal. This mystery polynomial that we're looking for, that's the value of c0. That's the value of c1. That is the value of c2, and so forth. That is equal to c3. and that is equal to Cn. And let's think about why that's true. So, how do we figure out what the C naught is? Well, before we plugged in 0. That's because we had powers of x's. These were x's instead of x minus a's. So now we got to plug in x equals a. So if you plug in a, that kills off. This is the constant term that survives. All of these get killed off. So in other words, this thing here is this is Tn of a. That's the constant term. Okay, so how do I find C1? Well, if I take the derivative of this guy, that goes away. This becomes a constant term because that goes away. And then I have all these terms, but if I plug in a for x, all of these terms get killed off as well. So this C1 term is just what I get when I take the first derivative. Again, that kills off the previous term. Plugging in a kills off all the remaining terms, and that's my C1. Okay, what about C2? To kill that off, or not to, I should say to pick that off, I'm going to pick off C2. If I take two derivatives, that gets killed off, that gets killed off. Good. This becomes a constant. Careful, what constant does it become? It's not C2 anymore. This, how do I want to write this? So I'm going to say this, Cn double prime. So let's take two derivatives and let's plug in a. And what happens? Again, these things get killed off. And when I plug in a, each of these gets killed off as well, because again, a couple of powers come down, but we still have an x minus a. So T double prime, I should say Tn double prime of a is actually equal to 2 C2. Again, because when I take two derivatives, the 2 comes down in front. Similarly, what happens when I take three derivatives of this? If I take three derivatives and plug in a, well, taking three derivatives kills off all three of these terms. And then all of the later terms, exponents come down, but there's still an x minus a. Plugging in a kills those off. So I'm left with just this term, and what happens? The 3 comes down with the first derivative, then the 2 comes down, and what I get is this is equal to 3 factorial C3. And so hopefully now you see the pattern that this really is 2 factorial there, and in general, the kth derivative of n, if I plug in a, is k factorial times ck. And notice that is where these factorials, that's where these things are coming from. And finally, again, I've been using TNs here and Fs up here, but as we saw before, we are looking for a function, a polynomial that matches F on every derivative. So this term must be equal to F of A. This term must be equal to F prime of A. This term must be equal to F double prime of A, and so forth. This is F triple prime of A. And this whatever this thing is, better be the kth derivative at A. Okay, so let's go back and finish an example that I hinted at before. Let's compute the fourth order Taylor polynomial of function cosine of x, centered at x equals 0. So before we start, let me sketch what this is going to look like. Oh, I don't want to use. Let me use black. Okay, so this is going to look like. So cosine looks like this. And the degree 4 polynomial, well, it's going to intersect at this, so it's going to look, probably looks, I bet we could find a polynomial that isn't exactly the function, but it's pretty darn close on this range here. And you can imagine if we were to do a degree 6 polynomial, we could get it to be close on an extra hump like this. Okay, so let's do this one using our formula from before. Oh, how do I want to? Oh, I'll do it down here. F of x is approximately equal to t4 of x, the degree 4 polynomial. So this is cosine of, this is the constant term, cosine of 0, plus negative sine of 0 over, let me before I do this, let me do a table. Let me do a table like this. Let me do n 0, 1, 2, 3, 4. Let me do the nth derivative of x. Let me do the nth derivative centered at 0. It's supposed to be n in there. And then let me do the nth derivative of 0 over n factorial. Okay, so the derivative, the 0th derivative of cosine, just the function itself, is cosine. The first derivative is negative sine of x. The second derivative is negative cosine of x. Third derivative is sine of x, and the fourth derivative is cosine of x. Great. Plug in 0, we get 1, 0, negative 1, 0, 1. And divide by n factorial, we have 1 over 0 factorial. Remember, 0 factorial is 1. That's 1. This is going to be 0. This is going to be negative 1 half. Negative 1 over 2 factorial. This is going to be 0, and this is 1 over 4 factorial, 1 over 24. Okay, great. So this is, okay, so this is the constant term. This is the first derivative over 1 factorial times x minus a, so that's just x, plus the second derivative. Maybe I will write out minus cosine. So this is the second derivative evaluated at 0 divided by 2 factorial times x minus a squared, plus the third derivative. That's sine of 0 over 3 factorial. That's supposed to be a 3 times x minus 0 cubed, and then plus the fourth derivative is cosine of 0 over 4 factorial x to the 4th. And of course now we can go back to our little table and plug in these values. And if we do that, we get, let's see, that's going to go away. That's 0, it's going to go away. And we get 1 minus 1/2 x squared plus 1/24 x to the 4th. So this precisely is this approximation right here. This is the best fourth order approximation to cosine centered at the point 0. So this function and cosine are indistinguishable if you look at the first 4 derivatives. So in terms of the value at 0, the rate of change at 0, the rate of change at 0, and so forth, 4 derivatives, these things are indistinguishable. You can only tell the difference when you get out to at least the 5th derivative. And now just for fun, let me revisit a question that I said earlier. What about the 3rd order Taylor polynomial? And I claim you didn't get anything better if you allowed yourself a degree 3 polynomial
versus a degree 2 polynomial. Remember, the degree 2 polynomial was a parabola that looks something like that. And now you can see it, that, well, I mean, I hinted at why a degree 3 polynomial is not going to be any better. But now you can actually see mathematically that that degree 3 term is going to be 0. So so the best degree 3 polynomial term is what you get if you get the first 3 terms, and you don't actually pick up a non-zero term for x cubed, because sine of 0 is 0. And this works for any odd term. If you want to degree a 7th order Taylor polynomial, that degree 7 term is going to be 0. Okay, that's it.